So it is now time. So we'll start. Maybe others will be joining. Very hearty welcome to our distinguished lecture series number 69 being delivered today by Professor Samit Kumar Rai, one of the finest person in the field. And this lecture, distinguished lecture series, is being jointly organized by Indian National Academy of Engineering, Bhubaneswar chapter, SOA University, IIT Bhubaneswar, NISER Bhubaneswar, IMMT Bhubaneswar, ICT IOC Bhubaneswar campus, and IEEE Bhubaneswar section. With all the effort of this group, we have now successfully completed 68 lectures, excluding 4 special lectures that we organized to celebrate National Technology Day this year. We hope to complete 70 lectures soon, and maybe by January 75 lectures. Now, today, the speaker is Professor Samit Kumar Rai, and his topic is going to be emerging semiconductor technologies, trends and perspective. A brief outline of his lecture has been already circulated to you, but for simplicity, I would just like to read a few lines from here. India has recently launched Indian Semiconductor Mission and National Quantum Mission to boost the economy and make the country self-reliant in all aspects. On the other hand, the progress in renewable energy sector has become significant in the last few decades. He will discuss the potential of some emerging semiconductor-based materials and devices for photonics, quantum and energy harvesting devices, the progress of emerging two-dimensional transition metal, dichalcogenides, inorganic perovskites, and their heterostructure for photonic and energy harvesting devices, hybrid heterostructures comprising of zero-dimensional materials on 2D semiconductors having excellent photosensitive characteristics offer the possibility to achieve next generation optoelectronic devices with superior functionalities. He will demonstrate all these things with his findings, research findings. He will also report the fabrication of color-saturated heterogeneous structure-based white light emitting diodes on a flexible platform. Finally, recent trends in piezoelectronics and tribotronics for self-powered flexible electronic devices he will discuss. Now, so far as actually Professor Samit Kumar Rai is concerned, he requires hardly any introduction. Professor Samit Kumar Rai is the chair professor in the Department of Physics, IIT Kharagpur, and he was one of my esteemed colleagues. He has previously served as the director of SN Bose National Center of Basic Sciences, Kolkata, Dean Postgraduate and Research Studies, Head Department of Physics and Chairman School of Nanoscience and Technology, IIT Kharagpur. His research interests are in the area of semiconductor materials and devices, quantum technology, low-dimensional materials, photovoltaics, and nanophotonics devices. He has served as a visiting faculty public scientist at the Tokyo Institute of Technology, Japan, University of Delaware, USA, University of Texas at Austin, Queen's University at Belfast, and Changchun University, Taiwan. Professor Rai is an elected fellow of Indian National Science Academy. Recently, he has been elected Indian Academy of Sciences, National Academy of Sciences, Indian National Academy of Engineering, and West Bengal Academy of Science and Technology. He is also the recipient of INSA Young Scientist Award, UGC Homi Bhabha Award, INA Chair Professor Fellowship, MRSI, Superconductivity and Material Science Senior Awards, etc. He has published more than 430 research papers in peer-reviewed journals and several book chapters. He is serving as an editorial board member of the Journal of Nanotechnology, Nanofuture, Scientific Reports, and Frontiers in Materials, Optics, and Photonics. So now actually I request Professor Rai to please make his presentation. After that, actually we will have question and answer.
Okay, sir. Thank you so much for nice introduction. So, and probably have to share my slides again.
Yeah, please.
Yeah. Is it visible now, sir? My slides?
Yes.
Okay.
Perfectly.
Okay. So thank you, Mr. Acharya. You actually have supported me a lot during your, particularly the leadership position at IIT Kharagpur. When I was building my lab, I was professor. Then of course I served as the head of the department during your directorship. So you really learned a lot from you. So today this is the very generic topic. So I may not cover everything that I have given in the abstract because I thought that time will not be enough. So basically I'll be talking about emerging semiconductor technologies and what is the trends. So I'll be talking mainly the global trends and of course perspectives, and then probably some of my research without going into very deep into that. So our research is always supported by different organizations like DST, MHOD, DRDO, MIT. So I acknowledge their contribution for this thing. Okay, so let me also have my pointer. Let us see, just me pointer option. Yeah. So let me get my pointer option. So what I'll do today, so initially I'll give you a little bit of historical perspectives. I mean, in this field, that why the semiconductor is growing so much over the last 5 decades or so, and what is the breakthrough that has already done, and what are there in the future, and then probably I'll talk about a little bit of materials aspects, and finally some of the devices of our interest. So particularly if I start a lecture for the students, I will always try to let him know, because we are grown up with all these technologies, where the bulbs were there, etc. There was no semiconductor technology at that time in the beginning when you were the students or kids. So some of the breakthrough inventions that has happened for the last 4 to 5 decades, as you see that, just I pointed some of them based on semiconductors. So this I am showing a typical silicon computer chip, microprocessor chip that we have in all our computer, mobile phone. And of course, so I acknowledge Intel for that, made of silicon. So this is the electronic chip. The next, this one is basically an optical device, called semiconductor lasers and LEDs. Of course, we have seen the laser in the lab, but all these lasers require very huge amount of power. But these semiconductor lasers or LEDs actually can be backed by a tiny power source, like a maybe 1.5 volt battery for a long time. And we see all the decorations in Diwali and other the marriage ceremony, you get now all LEDs. So these LEDs are nothing but tiny semiconductor junctions. So they're much more reliable compared to your typical the tungsten filament bulb or CFL. So their lifetime is much more and they take very less amount of power. That's why all lamps are being replaced by LEDs. And this is for the optical fiber communications. We know all our internet, particularly for local area networks, based on this fiber optic communications. So this also uses the semiconductor because the light source that you see here at the end of the optical fiber, actually optical fiber acts just as a waveguide. But you have got a source, you have got a detector, all are made of semiconductor. And next one may be energy. As I said, the energy also very important, because as you know that our energy based on the coals, etc., gives rise to lots of carbon footprint. So nowadays you can make a solar cells, and solar cells you can make a rooftop solar cell. That is one of the dream of the current government, the Prime Minister dream to have got ghar ghar mein bijli. So this is one of them. They should be much less power, and they really do not contaminate or the environment. The next in the future, last two are actually have kept some futuristic applications. The one is already being done. I mean, already being demonstrated by IBM, like a IBM quantum computer. Of course, here along with the semiconductor, one more materials comes. This is a device called superconducting quantum interference devices. So basically, it's a superconductor devices, but all the electronics are made of silicon or the semiconductor, so that you can have a very low noise detections of photons or single quantum bit. So this is definitely going to make a big impact probably the next decade or so. And probably in the future now, the scientists or researchers are thinking of making an integrated circuit chip how you can mimic the brain. So I'll show why it is when I go during my talk. Why this is right now, it's called brain-inspired computing, so that you can really make electronic devices which can mimic the brain. So I'll discuss this in more details in my talk. Okay, so why is suddenly so much of interest in semiconductor? It's not sudden, of course, it's there for a long time. But of course, now the semiconductor is more strategic, more important than the oil. So now the world wars are, of course, thought one of the things of the minerals, materials, semiconductors is one of them. And as you see the global application of the semiconductor, most of the applications, more than 60% is for the so-called computing, like data processing and network and communications. And maybe 1/3 of them for other things like industrial electronics, consumer electronics, automotive, government applications. And the growth is going to be huge actually. So this growth rate has been predicted. This is the 2024 prediction that 680 billion to about in 2030 it will be about more than 2 trillion. So average annual growth rate of more than 15%. But this target probably, or this prediction maybe still exceed this prediction because of the emergence of the AI, which we'll discuss. And fortunately, Asia Pacific has got a huge share of that, though India does not, at this moment, does not have so much of share. But as you know that Indian Semiconductor Mission has been declared. So we have already, the Tata Semiconductors are making fab at Gujarat. And there are lots of companies who are coming for the packaging, assembling of the devices. Chip design centers are already there. So India will soon have some kind of a good share among this 50% in Asia. So as you are saying that semiconductors are more important than energy resources like oil, because it's not world wars. If in the future is there, is already the tension, growing tension between China and Taiwan, because Taiwan is one of the hub for the semiconductor, and China wants to capture this because they're the building blocks of all electronics, microprocessor, GPUs, health, and communication technologies. This is very, very clear why it is so important. This slide I kept just for the probably some students' joys in mind. So how the technology has progressed in last 75 years. So this is the first transistors made demonstrated in the Bell Lab, discrete transistor, not integrated, around 1949 or so. So today we are in 2025. So 3-terminal device. This is basically the building block of all electronic circuits. Of course, with a much improved version. Within 10 years, the major electronic company at that time, Texas Instruments, we all use Texas Instrument calculator for our own in our student base. Within 10 years, they also make a first integrated circuit chip. But really the progress or the rapid development started from late 90s when the Intel come with a Pentium 2, Pentium 3, Pentium 4 processor. So it went up very, very rapidly. Okay. And these are just some of the people who are behind all these breakthroughs. There are many more. It's not all of, I've not shown all of them. The Shockley, Breton, and Bardeen, actually in the Bell Lab, they are the inventor of these transistors, got the Nobel Prize. And afterwards, 3 persons got the Nobel Prize around 2000. Herbert Kromer, basically on heterojunction kind of transistors. That means putting another material on a semiconductor substrate, and that has got lots of implications in today's communication technology. This is Alfarov from Russia. Actually, all these quantum wave lasers that you use in our laser pointer communications, even our medical stores and medical surgery. So that was also demonstrated by them. 3 of them got in the same year. And Jack Kilby, probably one of the first engineer, was given the Nobel Prize in physics because Jack Kilby at Texas Instruments demonstrated this fast integrated circuit chip. So there are very, very few Nobel Prize has gone to engineers. It is one of them. And of course, this is one more researcher at IBM in 1973. So actually, he discovered a new phenomenon called quantum tunneling in semiconductor devices. That is also a backbone of future quantum technology. Of course, as you know in history that we always say that at the point of time, nobody could understand his work. And the reviewers comment on his paper, which was rejected, is the work is too speculative and involved no new physics. So this is just a kind of a history. Now, where the India stood at that time? India right now we know India does not have much share of the so-called semiconductor technology. But of course, nowadays, last few years, we are trying to build fabs, trying to build companies. But historically, if you see that this person, all of you know this J.C. Bose, Jagadish Chandra Bose. Everybody knows that Jagadish Chandra Bose was basically the first person scientist to show the microwave communications or radio wave communications in 1894 to 1900. But not only that, for his experiment, he used semiconductor devices. He made a patent in, as you see, 1901, which was granted in 1904, which is much before the semiconductor transistor actually invented in the Bell Lab in kind of a 1949. He used a semiconductor material that time was not known. See, galena is a simple ore actually available in the Jharkhand area, Ranchi and all this area. So he was trying to define material and somehow he got some ore from this Jharkhand area, Ranchi area and put a metal contact on that and he could see some kind of a rectification in this device. So historically, this could be also pointed out the first semiconductor device which could really detect microwave from 12 to 60 gigahertz. So ideally, you see that the next the point contact transistor, which was discovered in 1947 or 49, is almost like his device or his system rather, as his measurement system. Almost like you have a chalk here, you have a chalk here. You put a semiconductor in Bell Lab, they put the germanium is known as the semiconductor. They put that something like that. Put a metal contact and took a current voltage characteristic to show that it behaves as a rectifier. But in this case, you could show that even with galena. So ideally, to see that this work would have deserved 2 Nobel Prizes, not even 1, because this detector using an unknown semiconductor There's the kind of a first semiconductor devices at that point of time. But anyway, so this is the history to motivate some of our young friends. They should know the history of science as well. But today, as you know, that most of the semiconductor breakthrough has given rise to rapid advancement in the quantum technology, or so-called computing technology. So if you see the computing system, this is the first kind of a computer in a Manchester University, UK in 48. And today, you know that we can have computer in our mobile phone itself. Okay, so this was a Views room with made of all valves, because these are not semiconductor devices; these are simply valves. So even many of these actual visionaries could not predict that semiconductor will make such a breakthrough about probably 70 years back, or 6 to 7 decades back. For example, Thomas Watson, he was the chairman of IBM. Actually, he's the founding chairman of the IBM. In 1940, he predicted that I think there is a world market for maybe 5 computers. So think of, and today is completely different. Every house has got several computers, because most of the mobile has got the power of computing also to some level. And the DEC, this is the Digital Equipment Corporation in 1977, in 50 years back or so. So his statement was that there is no reason for any individual to have a computer at their home. So at that time, I remember when I joined IIT Kharagpur as a student, there was a supercomputer made by DEC in 80s. So that was a supercomputer, the Digital Equipment Corporation. So the prediction was that computer will be only stationed one computer at IIT or any university, and everybody will be users of that. But you know that how wrong are these predictions, because the technology has progressed tremendously over the last 5 to 6 decades. So this is still a little bit of history that last year, maybe 1.5 years ago, there is a heading in the New York Times. The Gordon Moore, he was the Intel co-founder behind Moore's Law, dies at 94. So the question is that, okay, founder of a company dies at 94. Why should it be news in the New York Times kind of a first page? Because he predicted in 1960s that how these advances in computer chip technology or the semiconductor chip technology will give rise to some of the high-tech technology in the near future. So in 60s, he could predict. While Watson or probably Olson could not predict what will be this thing, but 60s he could predict, and he was the co-founder of the Intel. And today it is known as the Moore's Law. I think many of you have heard of the Moore's Law. The Moore's Law is the basically building law of the, of course, this thumb rule is a thumb rule, but it's a law of the so-called the electronic chip manufacturing. So it shows, so Moore's Law is basically going on for last 55 years or so. So it was in 1970, okay? So a semiconductor chip was made with a gate length of about, this is micrometer, about 5 micrometer. And today in 2025, this is made about 5 nanometer or so, commercially available. So 5 micrometer to 5 nanometer in just last 55 years, because of the advances of technology, because every generation chip comes, the size of this chip shrinks by about 70%, and the device density or transistor density is doubled, and the wafer cost increases, but the chip cost comes down by 40%. And you see every generation comes approximately out 2 years. So you can think about 25 different generations are coming over the 1970 years, from the 1970. Now the question is, what does it mean? This dotted line, this dotted line, or so-called the dashed line and dots. So the question is, here is the question of what is there in the future. So today we have got something called, suppose 5 nanometer of technology. Okay, 5 nanometer is a size of a silicon atom. So almost like atomic size. So the question is that, can we make a device whose size is less than the so-called the diameter of the silicon atom? That is the biggest answer that we have to find out. And probably that answers will come in next few years or so. But some predictions are already there. Nobody knows how they are going to make. This is a prediction beyond Moore's Law. So this is called the beyond Moore's Law. Okay, this starts from probably in the year from 2020 onwards. Okay, the current Moore's law, that one semiconductor company, because in Taiwan there is a semiconductor company called TSMC. They have the foundry for semiconductor manufacturing, and their share is more than 1/3 of the total foundry of the semiconductor in the globe. Okay, so if Taiwan is taken over by the China, actually the US will be the huge sufferer around, or US, Europe, and everybody is the huge sufferer. So what they have actually predicted, along with some other companies, this was predicted that in 2030 there will be more than 200 billion transistors per chip with the technology size about 1 nanometer. Okay, so they are aiming for a 1 nanometer technology. So the diameter is the 1/4 of the atom, and total transistor count can go up to 200 billion transistors per chip. So today we are somewhere here, about 20 to 50 billion or somewhere like this. All these are not commercially available. Many of them are actually in the R&D stage. Commercially, we are a little bit down. So maybe next few years, we have got 100 billion transistor per chip, and next 5 years, 200 billion transistor per chip. So they're also not happy with that. Actually, they are saying that now we'll do a stacks of these chips. We'll make just like PCB stacking. We can make a semiconductor chip, and we'll stack in a 3-dimension to make a 3-dimensional heterointegration, so that actually so-called board, on semiconductor board, okay, there can be about 1 trillion transistor per chip. So 1 trillion transistor per chip is very, very difficult to imagine, even if you have the number. But what we can say that all our mobile phone is nothing but a GPU server. We know that if you want to really do a very large scale computing or the AI, you need still need a supercomputer. So probably your mobile phone with a 1 trillion transistor could be almost like a functioning like a supercomputer. So this is the breakthrough that can happen in the next 5 years or so. Now, I have just used probably one equation in this slide. This is coming from the electronic device physics, that why the semiconductors are scaled down from so-called 5 micrometer to 100 nanometer to 10 nanometer, and then we are looking for 1 nanometer. The reason is, this is the building block of we know that is called complementary MOS transistor. CMOS means there is a 2 MOS transistor. One is actually we call the PMOS transistor, and one is NMOS transistor, integrated side by side, and they are connected and they make one CMOS circuit. And the distance between the source and drain of a transistor is called the gate length. So the physics says that if the gate length actually, if you reduce by a factor of K, suppose you reduce the transistor length from 100 nanometer to 10 nanometer, the device density, of course, will go 100 times as a K square. That is known because the areal density, the size comes down, of course, the area will be go as a square. That's fine. But what is interesting, not only that, the speed of the devices also goes up by a factor of K. So here you are getting 100 times more transistor, but which are 10 times faster. Because when you make the transistor smaller and smaller, their parasitic capacitance resistance actually drops down and gives rise to high speed. And more importantly, even if you have got a 100 times count more transistor, your power distribution is going by 1 by 100 times or 1 by K square. Because the devices are tiny, they require very, very low amount of power. So the final figure of merit for a so-called a CMOS transistor, how good they are, it depends upon if you scale down this length by a factor of K. This is called the power into delay. Power delay products as a 1 by K cube. So that means you have all advantage for by scaling down the transistor. So that's why actually the Moore's law initially called scaling down up to probably 100 nanometer or so. So now we are going to be beyond Moore's law, and in the next few years probably we'll be able to go to probably few nanometers. The technology is extremely very, very complicated. The only equation that I have written, that this may also come into in our discussions afterwards, the time delay T is for the device actually from this just a current equation, C dVdt equal to I. From there, if I just derive and write the MOSFET equations, we get something like L square by the mu. So mu is the carrier mobility. Carrier mobility means I apply an electric field in a semiconductor, and how fast actually they can move. That is basically, it's called the carrier mobility. So the T depends upon L square by mu. So obviously, if we reduce the value of the L, the time delay goes down. So that's the whole reason why you're going from 100 nanometer to 1 nanometer. But if we still have the limit, then you have to have a new material with a high mobility. Because if I make a materials like silicon, mobility is all well known, but silicon is not a very good semiconductor. But silicon is otherwise very good because of stability, because of other properties, physical properties. There are many other materials which has got much higher mobility than silicon, but they cannot be utilized. But in future, there is a possible that you need a high mobility material to make the device more faster. So basically, that scaling, if you scale down the devices, it improves not only the density, it needs speed, it improves the speed and power consumption of all digital circuits. Because we know we need high speed for internet, advanced gaming, processing, video files, communications. We want low power. We want more mobile should work for long hours after one battery backup. And of course, that you should have that cost should come down. So if you have a more transistor per chip, the cost will come down with added functionality. Okay, so but unfortunately, globally now it is a very the trend that is going. The trend is changing every 5 years or so. So the kind of the global semiconductor segments, if we divide into different kind of division, one is that kind of a cheap intellectual property. That means you have an idea for making a new semiconductor circuit or the chip electronic circuit. So this comes from, of course, this does not comes from industry. This comes from mostly for academic institutes, R&D institutes, and some of the of course it comes from industry as well. So once you get an IP of your chip, new circuit, then it's the electronic design automation tools. So as you see, the number of users actually or number of vendors actually come down. Then once it is done, then you have to choose the materials and subsystems. What kind of materials, what kind of technology that you'll be using. And once it is fixed, then of course the comes that you have to fabricate the devices. So this is called wafer fab. So you need lots of equipments. So these are the companies which makes globally the fabs. And India also does not have any equipment fabs also, because equipment fab is also a huge market. And then finally, these are the companies which make the chips, maybe a small fraction of the total companies, because fab is always very costly. So number of chip companies will be much smaller compared to the number of design companies or other companies. So that's what I said, that India right now have got one chip company which are building their fab at the Gujarat Sanand. There's the Tata Semiconductors. But another thing is the foundries. What the foundries do, foundries have all the technology available with them. They have standard software. So today I can design a chip at IIT Kharagpur. Okay, I have some idea. And since IIT Kharagpur or any other institutes actually have got Synopsys tool, Cadence tools, we can design the chip easily and give it to the foundry. And foundry will give you the device or circuits. So you don't have to go through all these things. So many of the companies are actually going directly from R&D level to directly to the foundries. But number of foundries actually, you see, this is a pyramid structure. Number of foundries are very small because people are not able to compete with the foundry technology. So yeah, this is very important data from Stanford University, USA that I have taken. You see, even 2001, okay, there are about 17 foundries when the technology node was about 130 nanometer. Okay, as soon as you came another 5 to 6 years, you see the number of company came down to 17 to 12. And you see there are companies from USA, Korea, Japan, Europe, as well as Taiwan, everything. But today we come back to this. Now there are only 2 foundries existing in the world. Okay, this is 2020. Today also like this. When the technology node has come down below 7 nanometer, this TSMC is a Taiwan company and Samsung is actually the company from Korea. So all the companies are making the Apple iPhone or whatever the Qualcomm chip design, Qualcomm chips or any computer chips. Actually, they are fabricated by them because the fab is extremely costly. So this becomes, and that's why a lot of money made by these companies. Like for example, there's a very nice story that we know that because of the AI, Nvidia is making a lot of money. This is one of the company it's actually revenue has surpassed the Intel. So Nvidia makes the GPU server, they make the GPU computer, but they don't fabricate anything. They just have the design and they go to the TSMC. And in Nvidia actually that revenue is much more than TSMC without making any semiconductor. Okay, so they make money just by the idea, design, and making these things. Okay, so this is a kind of I wanted to give you some trends. Now, while from there, I want to slowly enter to some emerging research field, and we are also contributing to some extent to some of them. So one of the scaling limit, of course, I still don't take that 3 nanometer, 1 nanometer technology. This is the, suppose in device scaling in 2024, commercially you have got all that so-called iPhone, Samsung phone has got a mobile phone. You have got 20 to 30 billion transistor in a mobile phone, and the gate length of the technology node is about typically 9 nanometer, commercially available. Okay, and each of the transistor takes a very small amount of power, 130 auto joule. Okay, about 10 to the minus 18 joule. So each transistor is really takes extremely low power to switch on the transistor. Okay, then we have got this circuit operates, suppose at a speed of about typically 10 gigahertz, like our state-of-the-art computer works, 10 gigahertz. So we are trying to calculate how much is the power consumption. So each transistor takes a 130 auto joule. The count of the transistor about 20 billion I have taken in this case, a very conservative estimate, and they work at the 10 to the 10 gigahertz speed. So this is the clock speed. And also not all the transistors are switched on at one time. Only 10% of the transistors switched on in a chip and 90% still in the switch off mode. So even if it happens, the power taken by the chip is about 260 kilowatt. So you are dissipating 260 kilowatt of power on a semiconductor chip of few centimeters square. So you can imagine what kind of a tremendous heat that will be generated in the chip. And if the semiconductor becomes hot, these properties got degraded, semiconductor can melt, and there can be always some alloys, diffusion takes place, so it may not work. So the question is that how still people are managing. Because people are still managing, they are designing very high quality heat sinks, they are designing high quality mechanical package. So basically you can say that now it's no more the challenge for the electronics, is challenge more for the mechanical heat dissipation problem. Okay, so can you use the fluids to dissipate the power? The answer is yes. So you don't know if it goes to 1 nanometer, you multiply by this, so it will be few megawatt of power that will be actually dissipated on the chip. So that is very difficult to, continue. So there has to be some kind of change. On the other hand, you have got, of course, emergence of AI of course, AI is there for a long time, but most of these things has been happening for the artificial intelligence, machine learning, etc. for the last 1 decade or so. Already we have got a lot of application, vision and language processing, self-driven vehicles, security applications, IoT applications. They are huge applications. But the disadvantage of the AI also you have to really keep in mind. AI is very power intensive, very energy intensive. They consume huge amount of power and give rise to very high carbon dioxide footprint. So this is a New York Times again prediction. The AI could soon need as much electricity as the entire country, maybe of not Indian country, maybe an European country or so. So whole world requirement of the AI is as much as that. So the carbon footprint is extremely high. So for an example, that just generating an image by the AI takes as much of energy as the full charging our smartphone. So this is not negligible because billions of people are generating, using this generating images or charging mobile phone. So the overall real energy consumption will be decided by how much AI you are using, not really how many vehicles you have or how much electricity you are using for your washing machine or car, etc. So that days will come. So this gives a very nice trends, as you see, over the last about probably last 10, 15 years or so. This is IBM supercomputer, kind of IBM version, Jeopardy in 2011. They used to take about 200 kilowatt of power. Okay? Huge amount of power, of course, the full supercomputer. Okay, as soon as the Google that DeepMind software for the AI software came, around 50s, about 5 years later, about 16, this uses this about 1200 CPUs and 177 GPUs. Yeah, it's actual number does not matter. What it matters, you see, as soon as you increasing the GPUs, you see the power is going, CPUs and GPUs, power is increasing by actually 50%. Now, today, or in few years back, now we have got ChatGPT 4, okay? So this has got 25,000 GPUs. 25,000 GPUs actually gives us just 60 megawatt of power. So this power includes the power that is used to actually back up these GPUs, and these GPUs or your nodes has to be always in the air conditioned room. They have to maintain the temperature with plus minus 1 degree, and huge amount of power actually you are dissipating or using. Now the question asks, what does your brain do? Brain also has got a huge amount of, as you know, neurons are actually the brain. We have got millions of neurons, and there are lots of neurons actually have got some kind of junctions with the brains at this thing, which also does the signal processing, which does a fantastic algorithm actually. I mean, gives us intelligence, natural intelligence, our capability of thinking, capability of sensing. So this has got about 10 to the 10 synapses per centimeter square. So about 10 billions per centimeter square. But our brain can do so many things, but it takes only about 20 watt of power. Of course, this power comes from our calorie that we take in the terms of food, of course, the glucose level, etc. So brain does a beautiful algorithm to solve everything in 20 watt. Of course, the GPUs and CPUs are much more faster than the brain. But as you know, algorithm-wise, the brain, or thinking-wise, the brain is still much, much better. So that's actually what is this technology is called that. Can we have a brain-inspired computing? So that is coming, that is one of the very hot area of the computer science and nowadays. Okay, so come back to the trends. All these things was more history, perspectives, and global trends. So from there are few areas which could be very, very interesting, particularly in the semiconductor technology. One is that, as I said, that make a 3D integrations at the TSMC has said that complementary FET, put the 3D stacks so that you can do hetero integration. That is one technology definitely. This is mainly done by the industries. And there's some emerging technologies like a photonic integrated circuits. Till now, we know what is electronic integrated circuits, but we don't know what is photonic integrated circuits. So we can, yes, we can use also the photon devices, can create photons and make their integrated circuits just like a silicon electronics. We can make a hybrid integration. We can make a silicon CMOS as a platform for memory logic, and we can bring many more materials into contact and make hybrid integration. So that is going to be very popular in future. And of course, these are actually the brain-inspired computing. As I said, this is actually AI-driven. It's called in-memory computing, and there are many more. So let me not go there. So why? So wherever I have shown some this blue highlighted layer means actually we have got some. We are doing some research on this field. We cannot do the research on really industrial technology, but this is still in the R&D stage. A lot of people are using this, so we are using on this. So why silicon photonics? Why silicon photonics integrated circuit? Because as you know, electronics, that the electron flows from one place to another. As soon as the electron flows, there is a lot of current. As soon as there is a current, there is a resistance in the circuit, so there is something called the heat dissipation. On the other hand, the photon does not have any charge. Okay, photon is chargeless. Photon is much faster because photon is basically quantum of the light particles. They are much faster. They have got the speed of the light. and they have got large bandwidth, which you're already using in optical fiber communications and our internet is based on already this kind of a large bandwidth to download the movie files, video files at a very, very fast rate. And if the two wires actually comes closer by, that there is no interference in case of a photonic integrated circuit. On the other hand, electronics, if the two wires are passing through close by and the current flows two wires, there will be lots of noises. But unfortunately, the technology is still not fully mature because, as I said, the silicon is the building block, silicon is the CMOS, but silicon is an indirect bandgap material. So you have to generate photon. Photonics means in case of electronics, you generate electron, you send some current through a metal semiconductor contact and inject electrons. In this case, you have to generate photons. So photons can be generated typically in a semiconductor. If the semiconductor is direct bandgap, you can generate like gallium arsenide, indium phosphide. So when you are seeing an LED device like LED, as I see, this is basically photon generator. LED generates photons. If you say lasers, laser generates lots of photons. But unfortunately, we cannot make LEDs, lasers using silicon because silicon is an indirect bandgap material, and there is a lot of other disadvantages also. So but on the other hand, you see, because of the data centers, because of the AI, the silicon photonics is growing almost exponentially. Okay, as you see, for the last 15 years or so, the use of silicon photonics comes only for the data centers. Because data centers, you have got a lot of servers, lot of GPUs, CPUs, and those can be connected by the photonic interconnects rather than the electronic interconnects. And as you see that this is also growing very, very fast. And most of the silicon photonics contribution is for the data center, this green one, and this one for the other applications. So this is possible the next decade or so. This will be also one of the technology that should be solve many of the heat dissipation problems that we are facing. So right now, since very quickly, I will show this is not our work. Right now, since silicon does not give rise to any photons, on the other hand, semiconductors like C5 semiconductors, gallium arsenide, indium phosphide gives you lasers. So basically, you make the lasers on indium phosphide, gallium arsenide, make your processor in silicon CMOS, then bring together at high temperature in an oxygen plasma. They form a kind of glue, and you just put one on them. So this is basically hybrid technology. This is not a monolithic integration. So the yield is very less, the cost is very high. So that's why still not a kind of a true silicon photonic integrated circuits. But many companies are already doing that. They are showing that I can have a chip here. This is a silicon photonics chip that can communicate using light. That means using photons. So you have got lots of areas where there are silicon memories, silicon logics, and you have got lots of optical components. Yeah, these are the optical components. Optical components, as you see, much, much larger in size. So optics and electronics are actually integrated together to give a new hybrid technology called silicon photonics. So if really someone come with invention to get a light emission or photon emission from silicon, that will be really a breakthrough, because then you can have a so-called computer which is called the dream is to have a photonic computer, so that huge kind of speed of the will not be limited to gigahertz or terahertz. You will go much beyond that. Now we'll enter thoroughly to a little bit onto silicon. I mean our semiconductor material system. Okay, so most of the semiconductors till now that you use are basically silicon. Most of the devices that you use for all electronic circuits are made of silicon, and silicon in the periodic table, they are called the group 4 elements. Okay, and there are other group 4 elements like carbon, germanium. So they are also semiconductor, but they are not as popular as semiconductor because of their cost and other stability. On the other hand, I told you the gallium arsenide, aluminum arsenide, indium phosphide. There is you take a combination, you take an element from group 3 and take an element from group 5. So you can make a 3-5 semiconductor, because one of the property of the semiconductor is that it must be having a covalent bonding. So covalent bonding means the average valency of 4. So this is the average valency of 4 electrons in the outer shell. Here you've got 3 electrons, you've got 5 electrons. So 3 plus 5 divided by 2 is 8, above 4. So this also you can take one from a group 2 element and group 6 elements. So we can combine them to make a. So these are actually called compound semiconductors. Like as you see here, we call elemental semiconductors, group 4 compound semiconductors, 3,5 semiconductors, 2,6 semiconductors. So today we have got lots of semiconductors, not only for the electronics, sensors, IoT devices, optoelectronic devices, laser, detectors, LEDs, and the technology is changing in such a way. We used to know from the childhood that oxides are always, kind of insulators. But nowadays that oxide is a good 6 elements. Like a zinc oxide is a very good semiconductor. Only thing you have to dope it properly and make it. The oxide also can be a semiconductor. Similarly, gallium oxide, aluminum oxide, because we are getting so many electrical vehicles into market, and they also need some kind of semiconductors which needs this kind of materials made of gallium nitride, gallium phosphide, aluminum oxide. So the whole paradigm is changing every year to depend on the application of the semiconductors. So I will not go to that. So what we do in our research group, we basically make an alloy of silicon and germanium. One of the reasons is that germanium was the first semiconductor which was discovered for making the transistor, and germanium has got much higher mobilities, much higher, better electronic properties compared to silicon, but unfortunately they cannot be processed so easily. So now today, by using a thin film growth technique, actually all semiconductor technologies are basically thin film technologies. We can make now different kind of thin films, making silicon germanium alloy, gallium arsenide semiconductors, all are thin film, not necessarily they are bulk. So silicon is bulk, germanium is bulk, but when you make silicon germanium, they are actually thin film. And the application is, so one application probably I'll show here, just in the photonic devices, not in the laser still now, but maybe in the detectors, because detectors is also important for the photonic integrated circuits. So one application, you see that detectors, the semiconductor, depending on the band gap of the semiconductor, we can detect the ultraviolet radiation. Visible is basically the LEDs that we get in the market. We can have a lot of infrared detectors. We can detect infrared. We can also have microwave detector. And in fact, the microwave detector was detected by the Jagadish Chandra Bose at that time. One of the most important wavelengths is basically optical fiber communication wavelength, which is about 1550 nanometer. Because at this wavelength, optical fiber does not attenuate any signals, and they can be used very, very efficiently. So this is one of our aim. And even if you take a simple example, today if you want to land in Delhi in a huge fog, normally a detectors with a visible wavelength, a responsive detector, the pilot will see a kind of a foggy atmosphere like that, and definitely he cannot land his plane or flight. Okay. On the other hand, as you see that if I go to detector wavelength from visible to near infrared, this range, actually this is called short wavelength infrared range, the thing is very, very clear. So I can have a camera which I can easily, and I can land my flight. So because they can see through the scattering media or haze media. Now the question is, when you go to far infrared imaging, you can even actually image at night actually. So there's no problem. So you can even image at the dark. And that's why actually you know that today Israel is one of the strongest country for fighting the terrorists. Because most of the terrorists actually or criminals are actually, they go to hide out in the daytime, they come out at night time, but they have got a far infrared camera, and from the far infrared it starts from about 12 micrometer to 50 micrometer. So they can actually image everything in the dark. So using this dark vision imaging, you have got a lot of, so this is a huge application for Indian and all defense DRDO, but India still does not make anything out of that. Okay, so just very briefly to our research, I will not go into the depth. As I said that we want to make detectors which are silicon compatible, because silicon has to be the wafer, they are CMOS. So we use different layers. On that, we want to make a fiber optic kind of detector made of material called germanium, because germanium band gap is around 1500 nanometer. And we grow this material by a technique in our lab, actually is called molecular wave reaction. It was actually installed long back, more than 35 years back, when Professor Chopra was here for the superconductor research. Then we converted to semiconductor. So when you grow this germanium and silicon, their atomic diameter is different. There is a mismatch of their so-called atomic diameter, and all this material has to be grown in single crystal form. So what happens, we start growing the material, lot of stress is developed. Just like a building, if a building is not well designed, there will be stress in the building exactly the same way. So beyond some critical thickness, actually, that the strain will relax and they will give rise to some kind of this kind of a nanoclusters, which you also call quantum dots. So if I can control the technology, I can have a germanium quantum dots of the size. And this is also clear from this is atomic force microscopy image. So we can easily get a quantum dot whose diameter is about 70 nanometer. Average height of this quantum dot is about 12 nanometer. And it can bring down to below about 10 nanometer or so. So in our lab, actually, we wanted to make some devices. There was a defense project, DRDO imprint project with MHRD. So it is a standard silicon technology. I have to make a transistors FET. On these things, this FET is a little bit different. What we did, we make a nanowire FETs. Okay, and nanowire, actually, the silicon nanowire is defined by a process called electron beam lithography. The diameter of this nanowire is in the range of 80 to 100 nanometer. And this nanometer diameter is actually ultimately, finally, after processing, we get something like this. So this is a silicon nanowire, which is decorated with germanium quantum dots. Now, silicon does not actually absorb in the optical fiber communication wavelength, but germanium does. So what we can do, we can use the germanium to detect the NIR photons, and use the silicon transistor to collect them. So that's what we do. So this is the finally fabricated devices. And you see that typical device dimension is around in the range of about 100 nanometer or so. And we basically make a field effect transistors. So I don't want to go into detail of that, but this works perfectly, the current voltage characteristics of a FET. And this has got different response to different wavelength. And we get the best response because of germanium band gap around 1500 nanometer. Okay, so that is very, very close to optical fiber communication wavelength. Now, of course, we have to see what is the gain. That means what is the responsivity. That means how much current can you generate, ampere you can generate per incident photon or per watt of photon. This is typically about 5 ampere per watt. Now, if I take a commercial silicon detector, if I go to the market, or commercial germanium detector, this responsivity is in the range of 0.1 to 0.5 ampere per watt. So already we have got actually 10 to 50 times more by using these nanowires. So by using nanowires and using germanium quantum dots, where the collection and generation efficiency is much more, we could go to much, much higher responsivity. So remember, it's about 5 ampere per watt, kind of state of the art. And from there, this is a defense R&D project. They want a kind of a prototype. We made an array of these detectors which could detect infrared radiation. Unfortunately, I don't know, my video files has gone a little bit of old. I could not search the original video files. Otherwise, I could have shown you that. But this is the breadboard. Actually, this is the breadboard. So our devices actually make like this and put in a package in a breadboard. And there is some kind of electronic circuits. And here you'll see that how much is the ultimately current. So this was the imprint project that we are doing at the point of time. So by changing the material from silicon germanium to, I think I will not go this, I'll just skip this because I have to also, sir, can I finish in another 10 minutes or so? Is it okay? Yeah, because I've started around 5:15 or so, so I'll not go beyond 6:10 or 6:15, okay? So, so we also make some other different materials, make nanowire and also make the devices. But here the responsivity or gain we get much, much higher. But I don't want to go to that. Rather, this is more interesting that now if you see the trend of the silicon electronics or photonics devices, if this is the roadmap, you see next 10 years or so, or next 8 to 10 years. So silicon is, as you know, that right now we are in the range of 3 nanometer, and we can go up to 1 nanometer or so in 25. This is a prediction, of course. This is a prediction 2022. And then we have to do some kind of a heterogeneous integration. Heterogeneous integration means we have to integrate new materials on silicon CMOS. So basically silicon CMOS plus X is the new material. We could say that the hybrid integrations, and that are useful for making circuits which is called more than more, then photonic integrated circuit, which I was talking about, the neuromorphic computing, quantum technologies, and maybe many other things. So some materials I am talking about, some two-dimensional materials. All of you have heard about the graphene. Graphene is the first two-dimensional materials that was actually discovered by Novoselov and got the Nobel Prize. Now question is that, can you use the graphene on another two-dimensional materials? Because the materials has got a very high mobility and some other properties, and we can get best out of the two. That means so sometimes we call the heterogeneous integration, or we can make a mixed dimensional heterostructures. So unfortunately, graphene, though, was the first 2D material. I mean, 2D material basically means the thickness of the material is much smaller than these lateral dimensions. So it's about 1 to 2 monolayer. Okay, but graphene does not have a band gap. It's not a very good semiconductor, so it does not absorb much light. So a new semiconductor class of semiconductors come. They call the transition metal dichalcogenides. So they are all well known. They're not new semiconductors like a molybdenum sulfide, tungsten sulfide, molybdenum silicide. These are all well known for long. Chemists prepare it, you can make crystals of them. But in the bulk form, they are actually, when they're in the bulk form, they are indirect bandgap semiconductors. But when you actually take a flex of the graphene, just the graphene-like flex, make a 1 layer or 2 layers, they actually they can be exfoliated to and they give this direct bandgap. So if I get a direct bandgap, really I can make the LEDs, lasers out of this material. Not only that, graphene, so-called 2D materials have got much better properties. They can be easily transferred to any substrate, with a flexible substrate, plastic substrate, metallic substrates, and they're flexible. So there are lots of advantages for that. So the research is going on in this area for more than the last decade. After this MOS2, WS2 has been, the 2D TMDC has been discovered. And again, we have got a number of materials with 2D materials, just like semiconductor materials. Some materials have got a very narrow band gap. So they work in the basically very infrared range. Some material got high band gap, which works as a very ultraviolet range. And there are lots of materials which works on the visible wavelength range. So you see that, so ideally 2D material is nothing but you can take a 3D crystals. Ideally, if you take a silicon crystals and exfoliate 1 monolayer of silicon by a Scotch tape that you use in the home, you get a 2D silicon. But unfortunately, 2D silicon is not stable, but these 2D layers are very stable. And they've got many exotic properties. So in our lab, actually, what we are trying to do for some time, for the last 8 to 10 years, working with a different kind of 2D materials and integrate on silicon so that I can make a heterogeneous integration. For example, the first of the work, suppose one of the work we did, tungsten sulfide, it's not necessarily monolayer, but as you see that we can take a sheets of tungsten sulfide and put in a silicon wafer, okay? And immediately we make a very good rectifying characteristics that shows that's a very good diode, because we take a p-type tungsten sulfide and n-type silicon, it can p-n junction diode, and one of the properties of the diode that it can give us a good rectifier, okay? So this is the input signal, this is the output signal. So that means you can use the electronic devices. Here is one more example that I will use that some other material called molybdenum sulfide I was talking about. So see, this molybdenum sulfide is prepared by simply chemical method by the chemistry technique. Okay, and if you really coat simple by spin coating on silicon, and you can make a device, PN junction device. You can apply a bias, the light comes out from that. You see the white light coming out from the device that was made in the lab. So that means that shows the direct bandgap material. If you can integrate successfully into silicon, they will give you the light emissions, which can be used for photonics applications. Here we have taken an example of that. These same kind of materials that you can basically take on a flexible substrate. This is basically a substrate called PET, just a plastic substrate. And as you see that we have given arrays of photodetectors, arrays of photodetectors on a plastic substrate. I can fold them, I can bend them, and I use two different kind of materials. One is the material is the silicon. Yeah, actually there is some silicon also there. Silicon has got some kind of a wavelength response in this range. On the other hand, 2D material has got a response in this range. So I can get a photodetector with a two different band selection lengths. So these are extremely important for many applications. So it's almost like this hybrid integration is just like making an atomic logo. You can make 2D on 3D, 2D, like this is 2D on 3D, 2D on 1D, or 0D on 2D, many things that you can do. So because these 2D materials can be exfoliated. So we also have done a lot of work to make it a two-dimensional materials to start with. And on that, we actually make a zero-dimensional materials. Zero-dimensional materials means basically nanoparticles or quantum dots or nanocrystals. So again, I don't have to, I'll finish by another 5 minutes or so. So here one material that you use, as I have talked in my, I've mentioned in the abstract, one more material called cesium lead iodide nanocrystals. So this cesium lead iodide is a material called the perovskite materials. They have come out very heavily in the last 1 decade because it has been shown that these nanocrystals can be prepared by all chemical method, and they have got much higher efficiency compared to silicon solar cells. So today, a cesium perovskite solar cell has efficiency more than about 35% or so. On the other hand, the silicon technology, which is very, very standard, probably cannot go more than 23% or so. So basically what we did, we made this perovskite nanocrystals and actually integrated on some kind of 2D substrates, like as I said, tungsten sulfide, and do a device structures. And from there, again, we made transistors, we made the characteristics. From there, actually try to find out what is the characteristics of the transistors, what is the characteristics of the devices we make. And now we get, actually by doing this, we get the responsivity is much, much higher, about 10 to the 4 ampere per watt. Earlier, I was talking about 5 ampere per watt to 50 ampere per watt. Now you see about 10,000 ampere per watt that we can be made, because 2D materials are very, very responsive, and perovskite has a very, very strong light absorptions. So basically, the people are also trying to make this responsivity in the level of about 10 to the 7 to 10 to the 8 ampere per watt. Then ideally, you can also detect a single photon, and that is the workhorse of the so-called the quantum technology. So my last slide for last 1 or 2 minutes, that the Nobel Prize was given, as you know, that neuromorphic chip, but the theory for them was done by this artificial neural network. It's there for, years together. We have got a lot of students. 20 years back has done a project to work on artificial neural network, ANN. But with the neuromorphic chip that is being fabricated, you can do ANN on the chip. And that's why the physics Nobel Prize was given in the Hopfield and Hinton. So basically it works like that, same thing. As I said, it works like a brain. The brain, you have got several millions of neurons per centimeter square. And when these two neurons join together, we call the synapse. So you have got about 10 billion synapses per centimeter square. So you make the question, this natural neuron exists in the brains. Now the question is whether you can make artificial neurons. Artificial is nothing but a kind of the connecting that how can you process the signal, whether I have got an electrical wire through which the current and voltage has to be passed. Normally in our body, as you know, that we have got calcium channel. Calcium channel gives the signal, and that's how we act. Our action is decided by the action potential. In the case of neuromorphic chip, we apply an external potential and do the same thing. And the industries are also taking it seriously. As you see, the Intel Lohi 2 chip supports about 1 billion neurons with a 120 million pair synapses. So we are coming very, very close to the mimicking the brain. So this is actually necessary because traditional computer is designed in a von Neumann architecture. Okay, so von Neumann architecture is there is always a processing unit for that we call the arithmetic logic unit, where all the arithmetic things are done. The results are actually passed through, data are passed through, and data are actually stored in a memory. So we have got a memory as well as a processing unit. This is one computer. I mean, on computing these things. But our brain does not have that. Our brain have everything in these things because of brain, memory, and processing in the same location. So this is actually they are calling the in-memory computer architecture, because as soon as the data flows, there is a lot of power. Okay, there's a lot of energy, a lot of delay. So this is called actually memory wall bottleneck in a conventional computer. So still we are making the GPUs with the conventional circuits, but in the future, the circuits will be made like this, where actually you have got some area where there will be control unit, the data processing, you have periphery, you have got interface, and you have got memory and processing together. And this can be done in a semiconductor chip. If you have some kind of a device, it's called memory stud devices, the metal and insulated. And if you just make a crossbar architecture of all of them, we are talking about billions. So billions means about 1,000 by 1,000 array, isn't it? Or yeah, I mean, sorry, 100 millions with 1,000 by 1,000 array. Billions will be a little bit more than that. So actually, it's a million by million. So you make an arrays of these transistors, and you interconnect in a crossbar array. And this device actually remembers. This acts as a memory. So if I take a current voltage characteristics, I have initially as a very, very low current or a high resistive state. Then at a threshold voltage, very small voltage, go to low resistance state. So this is we call logic 0. This we call the logic 1. Now, even if I switch off the power, the logic 1 remains until and unless I give it a negative voltage to switch off the memory to go to the high resistance states. So this is called memory resistive devices, and this can be done by many semiconductor materials. And we have used that perovskite materials to show that switching, and you see that within 1 volt we can go for switching, and then we come back, then we can actually close. This we have got hundreds of measurements. As you see, there are a little bit of non-uniformity that is possible in the lab scale, but that is what actually you have to standardize. So this digital safe switching, on the other hand, is the analog switching. You apply small amount of pulse, it goes somewhere. If you small amount of pulse, it goes somewhere. So this is kind of an analog computer. So in the brain, you have got both digital and analog computer. So you have to mimic them. So basically, the idea is like this: you have different kind of materials. We have used cesium lead bromide, but you can use a uptin number of materials. Just mimic like a biological synapse. Once you get a response like this, the response is if I'm getting a voltage pulse, same voltage pulse for different time, the current level is going up. It is something like that. If I read a book for 5 times, I'll remember that one paragraph of the book. If I read a book for the first time, everything I'll forget. So basically, is going from a short-term memory to long-term memory that you can actually implement in the chips. So yeah, these are many. I'll not go into the details because already up. But some of the application, very, very common application, that is a digital recognition, or image processing. In this case, we have taken from MNIST database, we have written hand digit of 6. So we have a 20 ONT, we have divided into 28 into 28 pixels. So input layer is about 784 nodes. Then, as you know, neural network, we have got some hidden layers, about 128 nodes. And ultimately, we could accurately predict the number is 6, about probably 95% or so. So this is actually test accuracy. So probably I will stop here, and a summary of my lecture that what we have discussed till now, the trends and perspectives of semiconductors. So this is the trends. So today we are going from about, say, suppose nanoelectronics started from 1990 with 90 nanometer in 2005 or so. So today we are here in the range of few nanometers, like 3 to 5 nanometer. And the future, when the integration limits will be saturated, then we have to have more and more materials integrated. So that's for the hybrid integration. So let me thank my group of students also, whatever research data I have this thing. But of course, my group has now trimmed a little bit. It's not right now only about 8, not over 12 or 13. But they are the members of the microscience lab. I really thank all of them for any contributions that I presented today. So thank you so much. So I'll be very happy to take up any questions that we have. And sorry, I had to go a little bit faster because I want to give a little bit more coverage.
Thank you, Professor Raj, for your excellent introductory lecture that you gave. At least it was a sort of eye-opener for me, a layman like me. Now, in fact, your lecture was very, very interesting and illuminating. Now, I would like to invite some questions from the audience. First person actually who has shown interest is our old friend, Mr. Sanat Kumar. Please, Sanat Kumar ji, you start the ball rolling.
Yes, sir. Thank you. You got the wrong person for electronics. But anyway.
No, I mean, nobody is wrong. Everybody is right. We are
Okay.
here.
As you were giving the lecture, a thought crossed my mind, a purely a mechanical mind. So I am asking this question. It may not be relevant. See, you said in a chip, you will have 1 trillion transistors. I would imagine each transistor requires 3 lead wires. So 3 trillion lead wires you have to connect. How do you do that?
Sir, it's an extremely good questions. So excellent questions. Right now, of course, not 1 trillion. Right now, let us say 50 billion. Okay, but future is 1 trillion. Yeah, there actually comes the one technology called the, as you know, the VLSI design. Okay, this is a very, very sought after area. So basically, what do you do? How do you connect these things? If you try to connect those transistors, even 1 million transistors, and if you get the metal length that you need to connect, it will be probably few hundred kilometers. And you have got only few centimeter by few centimeter chip. So what is done actually is a multi-level metallizations. So technology is like a 7 to 8 levels of metallizations, and VLSI designers will design that how the layout. This is called actually VLSI design. They will do the design that how this wire will go and connect to this. So they will completely do the design, and that's why they are paid so much of money in the industry. They are the highest paid people in the industry, because they have to make a topology layout in such a way that you can really connect this so-called 20 billion, 100 million billion transistors on the chip with the available in the these things. And please remember, I cannot connect 2 wires. If I connect 2 wires, everything is shorted. Okay, so I have to isolate them and connect. So this is a huge problem. So this is done by multi-level metallization in the experimentally, and design is done by the VLSI engineers. That how the, in fact, it is like if you see the picture, I didn't have the picture for a blind. It will look like is a multi-storied building coming one after another, and how the pipes goes on. I would suppose the gas pipes, electrical pipes, cables goes on from 7th floor to, I mean, probably first floor, ground floor, almost like that, but different level.
Okay, sir. Thank you. Thank you very much. I will go through this a little bit more, look at some books and find out. Thank you.
Sure. Thank you.
Okay. Next.
Sir, can I ask one question?
Please.
Please.
Thank you, sir. Sir, I want to know that in what way does the band energy engineering or the heterostructure design help in minimizing the black current loss?
Dark current loss. You're saying dark current loss, no?
Yes.
Yeah. See, the why do we do band gap engineering? The one example I will take, suppose optical fiber communication. Okay, as I said, it takes 15-50 nanometer. But unfortunately, no natural semiconductor is available with that band gap. So what I have to do, I have to take a gallium arsenide semiconductor, make a aluminum arsenide, and actually make an alloy so that the band gap is like just a mechanical alloying. So gallium arsenide is some band gap X, aluminum arsenide is some band gap Y. If I take a 10% of that, 50% of that, I will have a, so that my energy band gap of the alloy becomes, or the compound becomes exactly 1.155 nanometer. You are correct. As soon as you make an alloy or compound semiconductors, there is always a problem of non-homogeneity. There will be all, it will not be homogeneous. There will be some defects created. So if the defects are created, your dark current will go up. So that is the biggest challenge, that you make the material without creating any defects. So that's why you have to use a very, very sophisticated epitaxial growth technology. Now, one technology I have shown MBE, but industry, they have done something called metal organic CVD, MOCVD. Professor Acharya also may remember DN Bosch had a MOCVD system. So you need a similar layer, but the crystalline quality has to be near perfect. The better is the crystalline quality, lower is the dark current.
Sir, can do 2D material like MOSO2 or Gefine offer solution for controlling the black current in ultra scale transistors?
Yes. Now people are reporting. In fact, we had also some report, but our dark current was not so low. But now people are reporting that 2D on 3D heterojunction, the dark current they are reporting is almost like that's like a pure silicon transistor. And there is a group in Penn State, one of the Indian is working, Saptarshi Das, he's one of the masters on that. So in a few months back, their group has demonstrated almost like a 2D CMOS computer. It's not a full computer, it's a prototype that it can do a CMOS logic using a completely 2D material. So this is possible, but actual technology will take time. So 10, 20 years, as you know. Developing in the lab stage and developing in the commercial is completely different thing.
Yes.
But the Sarangi had asked me, thank you. But Sarangi had one question that what is the current in the semiconductor, something like that, probably, because probably his things are not working. So, sir, that whenever, because all these electronic devices, I have to apply some voltage. Apply some voltage, that means there will be always some current. In fact, a semiconductor switch, the first basic building block is a semiconductor switch. If you talk about digital circuit, I have got to have two states. One is zero states. So zero state is ideally no current, but there will be some dark current, as madam just pointed out now. And one state means there is some finite amount of current. So I have to switch the logic between transistor between 0 and 1. So for that one to create one, I have to apply the voltage, I have to apply pulse. Immediately some current will flow in the circuit, and that will give rise to some one state. So basically this happens due to the flow of electrons and holes. If I apply electric field in semiconductors like silicon, if it is N-type, there are more electrons, if it's P-type, more holes, they will start flowing through electric field, and that will give rise to some current.
Okay.
Sir, I have a
Dr.
query.
Sanjay Kumar Sarangi, would you like to ask some question? Dr. Sarangi?
This was Professor Sarangi's question. What I answered was Sarangi probably is the problem in his mic or something like that, or microphone. What I answered is Professor Sarangi gave a question in the chat box. I took from there that what is current conductor. Yeah.
Professor Kulamani Parida?
Sir,
Would you like to ask some question?
Sir, this is that evolution of semiconductor chips from 90 nanometer to 5 nanometer is based on silicon technology or some other materials is used?
So this is completely silicon technology. Now what we presented, those with commercially only silicon technology, okay, for electronics. These are all silicon. But of course, gallium arsenide also you can make, but they are not competitive in terms of cost. They are not competitive in terms of performance. So all mostly is the silicon technology. 95% of the devices are silicon.
Sir, one more query. Sir, photovoltaics, you told about silicon metals and halide perovskites.
Right.
This halide, why only there is no so far there is no substitute to the silicon technology. This halide perovskites, though everybody is claiming is a very good materials, but is not replacing the silicon
True.
metal from the photovoltaics.
It's true. Yeah, one of the problem with the halide perovskites are actually they are actually not very stable. So they degrade in sunlight and they degrade in a humid environment. So whatever demonstration people have done right now after packaging, etc., but the lifetime of the shell is not very high. So that's why it is still can be used for indoor application, but not under the sun. So it's true that silicon is the only technology commercially available, but the problem is that silicon technology is very, very costly. Okay, and on the other hand, these materials that we have used in halide perovskites, all these materials are very cheap materials. They're earth abundant. They are used readily available on the earth surface, and they can actually prepare commercial. I mean, by chemical method, and you can coat on a plastic substrate, and all this plastic substrate is like a solar cell. So that is for large area, cheap, flexible, but still is not commercialized. You are right. You're perfectly
So
all
one
right.
more,
Yeah,
thank you, sir. Thank you very much for your nice clarification, sir. One more question is not relevant to very much relevant. Just for my inquisitiveness, I am inquiring. But India, why you are not so far capable of developing such a very clean room to process all the semiconductor materials? We don't have
Okay.
very good clean room.
Sure, sure.
Recently, this our IIT Bhubaneswar, they have been making some press news.
Right.
Why you are lacking in the semiconductor processing? Because we are not so far developed a very good clean room in India.
See, one of the, I'll say generally fab, not only clean room fab. 1984, what fab was created at Semiconductor Complex Limited, Chandigarh. Okay, so there was a fab. That time the technology was probably something like that, maybe about 180 nanometer technology or something like that, or maybe a little bit less than that. What happened then? There was an accident. By the time the chief started working, there was a big accident. So actually, there was a probably that hydrogen gas, there was an explosion and a whole the lab burnt out. So one of the, but that is one accident, forget it. The other thing is basically the cost, because all the semiconductor material, they're extremely pure. They're 9N purity materials. India does not produce them. All the chemicals, gases, wafer fabrication equipment are not available in India. So as you see, not only India, most of the European countries and US countries, many companies are actually had to wind out because of the Taiwan and so-called the TSMC. Even the Intel, which was going very, very high till about some 5-6 years back, they have to actually closing their fabs because it's extremely cost intensive. You have to really invest lots of money. And fortunately now India has actually decided to invest something, because during the COVID time we have seen that you cannot, we had a queue for buying the automobile vehicles because all automobiles are controlled by the electronic chips. So if you remember that many people are saying that we are not getting the silicon chip from China. So China did not have control. So that we are not dependent on China. Now India has started. But definitely we have started late. But better late than never in the future, so that we become self-sufficient.
Thank you very much, sir, for illuminating talk and this talks very fundamental things for our clarification. Though we are not very much
No.
concerned on semiconductor materials,
That's
but
true.
some
Yeah, good to
other
see.
other
Yeah.
semiconductor materials have been doing.
Yeah, good to see Bhubaneswar Zone will have a fab, and this will be made of silicon carbide. I was talking about silicon and carbon together in the group 4. So they will basically give rise to silicon carbide devices, which can be used for high power applications like automobile charger. Automobile charger draws a huge amount of current, instant current. So you know silicon carbide. Then lots of power electronics they will be used. So that is a very good strategy to start with a new material. Very good.
A lot of work has been carried out in IMMT Bhubaneswar on silicon carbide, but they have gone up to certain stage. That means they have, then after that they have stopped it.
Actually, they are not electronic gate. Electronic gate means you have to this thing, your impurity has to be parts per, maybe 10 parts per billion or something like that, 100 parts per billion. Otherwise, this semiconductor will not work, because any defects, contaminations, all these electron and holes you are creating, they will actually get trapped, recombined. The device will not work. That is the main reason.
Okay, thank you.
And Dr. Chandrasekhar, would you like to ask some question? You have been waiting for some time. Any other question? Okay. So Professor Rai, it was really very, very illuminating, and discussions were also very, very useful. And now, before I request Madam Renu Sharma to propose a vote of thanks, I would like to say that your lectures has been really recorded. Will you permit it to circulate through the members through INA? If
So no
you say
problem.
yes, we'll do it. Otherwise, we will not.
I think yes, because only problem is sometimes I try to give the references to all the slides that I have taken from others' work. I try to
It's okay.
possible.
That you have already mentioned also.
Yes, I tried, but there may be always some, I missed something, may happen, always happen. So the problem is like that only, otherwise I have no objection. So because nowadays actually, the copyright, etc. Suddenly people will say that you have presented my slide without my permission.
No, this is not actually the copyright question. The question is actually if you have used certain information actually which you would like to keep to yourself, then it is a thing.
Yeah. And this is also I know that this is a kind of academic lecture, no commercial interest.
It is academic only. That is up to you.
So I have no problem, sir.
If you permit, actually will circulate, otherwise not.
Yes, I normally what you do? You do to all INE members, or what do you do normally?
No, it is actually they are all recorded and circulated through YouTube. We give a link only.
Okay.
The actual thing is actually with us.
Oh, I understand. No, I have no problem. I think I have given more or less acknowledgement to almost all the work, and our own work is anyway published, so it should be all right.
No. Many people actually have said that no, there is no objection. Of course, one or two exceptions are there where some confidential information was being used.
No, okay. I didn't give any confidential information. So it's okay, sir.
Okay, thank you so much. Now, may I request Madam Renu Sharma to please propose a vote of thanks for this excellent lecture. And one more information that I would like to share, that the School of Nanoscience and Technology under the leadership of Professor Samit Rai is doing exceedingly well work in IIT Kharagpur, and that was really established with a special grant of some 200 crores that we got from the government of India.
Diamond Jubilee. In
Diamond Jubilee year.
Yes. That's what that
fund it was established, not only this one, and many, and 3 more other actually schools in all emerging areas.
Right.
So, and it is actually Professor Rai who has really spearheaded it as its head and is doing exceedingly good work today.
Thank you so much.
Okay.
At least we had the vision. You created 4 schools: bio school, nano school, energy, and environment. I remember.
Yes,
so
yes.
All of them were running.
Yes, all of them are actually doing well. So, Madam Sharma, please.
Sir. Thank you, sir. I'm audible, sir?
Yes.
Good evening, sir. Good evening to all. It's my pleasure and honor to propose a vote of thanks on behalf of Indian National Academy of Engineering, Bhubaneswar chapter, jointly with Shiksha Anusandhan deemed to be university, CSIR, MMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, ICT IOC Bhubaneswar campus, and IEEE Bhubaneswar section. At the outset, we express our heartfelt gratitude to Professor Samit Ray, Professor, Department of Physics, IIT Kharagpur, for delivering a truly enlightening lecture on the topic Emerging Silicon Technology Trends and Perspectives. Sir, the insightful talk provided us an in-depth understanding of latest advancement in semiconductor material device technology, their implications for future innovations. The clarity and the depth of this presentation was certainly enriching all the participants, those who have participated and those who will be listening through the recorded message. We sincerely thank all the distinguished dignitaries, fellow members of INE, faculty members, researchers, students, and all the collaborating institutions for joining us in this virtual session and making it as a great success. And once again, I extend my deep appreciation to Professor Samit Ray for sharing his time, knowledge, and experience with us, and to involve everyone with the question and answers as a part of 69th Distinguished Lecture of the series. Thank you all. Have a pleasant evening. Namaste. Jai.
Thank you so much. So I had a privilege. Okay, sir. Bye-bye.
Namaste and good night.
Namaste.
all of
Good
you.
night. No, that's all of you. Thank you. Thank you so much. I'll leave now. Huh?